All right, welcome everyone to our first lecture on our introduction to biomechanics and motion capture. I am Derek Lyra. Again, I'm an associate professor in the bioengineering program here at FGCU. First of all, I'm going to go over the basics of biomechanics. Really, the basics of biomechanics is the same as classical mechanics. And classical mechanics is basically Newtonian mechanics. And the application of Newtonian mechanics to biological problems is commonly the field of biomechanics. So it's important for us to first understand the three laws of Newtonian mechanics. First law being a body at rest will remain at rest, and a body at motion will remain in motion unless acted upon by an external force. This basically means that if there's no forces acting on a body, it will continue on whatever its current path is, or if it's not moving, it'll just stay still. The second law is the forces acting on an object is equal to the mass of that object times acceleration. We typically see this expressed as force is equal to mass times acceleration. But we can also write this as acceleration is equal to force divided by mass. Basically, the force acting upon an object is going to be proportional to its mass and its acceleration. And then the third law, for every action, there's an equal and opposite reaction. Basically, if you have two objects that are pushing, or one object's being pushed, there has to be an object doing the pushing, right? So basically, you have an equilibrium of forces at all times. So we're going to look at an example here of a ball. So we have Mr. Ball, and we have Mr. Ball is just any object with a known mass, right? So if he's sitting with no forces acting on him, he stays in the same place, right? So here Mr. Ball's on the beach, and so there's no forces acting on him, he's not going to go anywhere, he's just going to stay there. So he's going to stay at rest. If he's rolling along on a path, then he's going to stay in motion, right? Typically when we have an object moving in real life, friction with the air and with the ground will bring that body back to rest because it acts in the opposite direction of the direction of motion. But if this was a ball in a vacuum, then it would just continue along its path and only be affected by things like gravity, right? So keep that in mind. If we have an object at rest or an object in motion, it's going to stay in motion. Now, if we have a force acting upon the ball, it's going to move or it's going to accelerate, right, in the direction of the applied force. And that acceleration is proportional to the force and inversely proportional to the mass. So we can say that the force is equal to mass times acceleration. Again, we just talked about this. Or the acceleration is equal to force divided by the mass. That means that the larger the force, right, the greater the acceleration, the larger the mass, the less the acceleration. So the mass resists the force or resists the acceleration, right? That's why we refer to the mass as the inertia, right, of the object. So for a ball of constant mass, the harder you kick it or the harder you throw it, the more it will accelerate during the impact and then the farther it will go. Before we get into kind of a full analysis of force and acceleration, the first thing we're going to look at is the kinematics of an object. And that's really just studying the motion of the object. Because again, if we know the motion of the object, then we can calculate the forces that are being acted upon it. And in biomechanics specifically, a lot of times it's hard for us to know what the motions or what the forces on bodies in the biological system are. But if we know the motions, we can record how they're moving. We can predict what the forces should be based on those motions, right? So we have the kinematics just measuring the position, velocity, and acceleration, right? And all of these are related to each other by time. So velocity is the derivative of position, and acceleration is the derivative of velocity. So if we know one of them, and if we only know acceleration, we have to know what the initial velocity and the initial position are. So if we know one of them and we know the initial state of the rest of them, we can calculate the other objects. So this can be expressed in a couple different examples here. This is probably the simplest example. Here we have a ball, an object moving along a constant path, or a linear path at a constant rate, right? And we can use the discrete difference functions to find the velocity of a given position in time, right? So this is a position of the ball in x and y coordinates. So you can see here we have a x coordinate system and a y coordinate system. And this ball is moving in the x, but it has some position in the y. So this table here describes the position of the ball at time 1, 2, 3, and 4. And so at time 1, it has an x position of 2. Then at 2, it has an x position of 4. And at 3, it's got an x position of 6. And at 4, it's got a position of 8. Then the y position is constant the entire time, so it has a y position of 6. Right. So if I want to know the velocity of this using the forward difference, I can look at, okay, well, at time 1, the position is 2. And at time 2, the exposition is 4. Therefore, velocity, which is the change in position over change in time, we have x2 minus x1, which is 2, and then t2 minus t1, which is 1, because 2 minus 1 is 1, right? So we get 2. And so we can do that for all the different positions. So 4 minus 2, that's 2, divided by 2 minus 1, which is 1, that gives us 2. And if I do the same thing 4 times 2 and times 3, and I can't do it for times 4 because I don't have a time 5, right, then I can calculate the velocity these times. It's important to note that this doesn't actually give us the true instantaneous velocity. This is a discrete forward difference. So what we're doing is we're getting the average velocity from time 1 to time 2, and then we're treating that average velocity from time 1 to time 2 as the velocity at time 2. So the larger the increment of time we have here, so if this was, 20 seconds or 30 seconds or 40 seconds or a minute, right, that might be very inaccurate depending on how much this ball is moving. In this case, it's moving at a constant rate. It's probably pretty reasonable, right? Then again, the y isn't moving. And then we notice here that as we get a constant value for velocity, so 222, if we do the same thing again, repeat the forward difference to calculate acceleration, we can do 2 minus 2, which is 0, over 2 minus 1, which would be 1. We do that. Also, to prevent this from creeping, because you can see that if we were to do the forward difference again, we'd have two unknowns here at times 3 and times 4. We can kind of balance the forward difference when we calculate acceleration by using a reverse difference or a backwards difference, or rather than taking the time 1 and time 2, I can take time 2 and time 1, basically treating the average from 1 to 2 as the current time at 2 rather than the time at 1. So it shifts everything forward 1. But you can see we do lose a little bit of data every time we do this, and there is an accuracy in this because of the fact that we're treating the average velocity as the current velocity. So one other thing we could do if we wanted to, rather than using this discrete difference, we can actually go through and we can calculate this as a function. So in this equation here, we notice that the function x of t is equal to 2t perfectly fits the path of the ball in this example. So the x position here is always just 2 times the time value. And that's an artifact of this being an example. Normally you wouldn't get a perfect fit on something like that, but you would get something that's reasonably close, right? So if we have a function for the path of the ball, we can actually use calculus to find the velocity and acceleration as a function as well. Now we actually won't be using the calculus version of this for any examples in this module, but it's important for you guys to understand how this works, and you'll apply this kind of throughout your career as engineers. So if I take the function x of t is equal to 2t, and I want to find the velocity of x, which is equal to the derivative of x as a function of time, right? And we can express this as x prime. We can also express it as x dot, but there's lots of different ways of showing the derivative. So the definition of the derivative is the limit as the change in time goes to 0 of x of the current time, or t, plus the change in time minus x of t. And you'll note that this looks a lot like our original equation that we looked at before. We have, if we had dt as 1, right, and we went from 1 to 2, we have x of 2 minus x of 1 over x of 1 minus x, or x of 2 minus x, or time 2 minus time 1. And so this would resolve to the discrete value. But again, we wanted to make this delta t very, very small, so that way that error from that time difference basically goes to 0. So if we do that, again, I'm going to substitute all these things in here. So we have 2t, so I'm going to substitute in the t plus dt for t for this one right here. Then in this one, we're going to substitute the 2 in for the t in for the second equation. Then we're going to divide by our delta t. And we're just going to simplify this. I'm going to distribute the 2 across. You'll note that we have 2t plus 2 dt minus 2t. So the 2 t's are going to cancel each other out. And we left with 2 dt over dt, which if they cancel the dt's goes to 2. So the derivative of this 2t function is equal to 2. And there's lots of simplifications you can use for solving for polynomials and different equations. But again, we're not going to get into that too much. But so we can show that derivative of 2t is equal to 2. And that makes sense because if we go back and look at our discrete, we see the velocity here was 2, right? So it doesn't matter how we did it, using the discrete method or using calculus, we get that the velocity in the x direction is basically a constant 2. So that's a very, very simple example, but we can go move it a little bit more complicated by looking at a parabolic arc, right? So this is what would happen if you were to throw a ball the initial velocity in both the x and the y direction, and we neglected friction. So in this case, the velocity in the x doesn't change, and the velocity of the y is only going kind of down by the acceleration of gravity. And these are not using any units currently, so this gravity is kind of an arbitrary -2 in the y, but you could use, whatever you want for the example here. So again, this path has a similar constant velocity in the x, but also an initial high velocity in the y that decreases until inverting it comes back down. So basically it starts going up. As it's going up, it's accelerating downwards, so it slows down until it stops, and then it accelerates back down. Again, this is a classic example of parabolic motion. You see this tons and tons and tons in your general physics courses, so some of you may have already seen this several times. But again, if I describe the position of this ball in x and y coordinates, we can see that the x is linearly increasing, so it's just 2, 3, 4, 5, 6, 7, 8, 9. Well, actually, there's no 9, it stops at 8. It's linearly increasing, so it's staying constant. And the y, it starts off with larger changes, so it goes 2, 7, 10, 11, 10, 7, 2. Then again, I can use my forward difference to calculate the velocity in the x and the y. So again, here at time point 1, if I do 3 minus 2, that's 1, divided by 2 minus 1, which is 1, so I get 1. And you can see that goes through all the rest of the way. And then for the y direction, if I do 7 minus 2, that's 5, and then again divided by 1. And then again, I can do 10 minus 7, which is 3, again divided by 1. I can keep doing that. And then in the acceleration, if I do 1 minus 1, I get 0, so that's pretty straightforward all the way through. And this one here, I can see that I have 3 minus 5, that gives me -2. And again, since I'm doing the backwards difference here, I put that in the time 2 instead of time 1. So I can do the forward difference for velocity and the backwards difference for acceleration. This kind of balances those errors out. And we can see we have a constant acceleration in the y direction. So hopefully that makes sense. And what we're going to do next is I have a few videos on Khan Academy that you guys should watch. And those will hopefully give you a little bit better understanding of the principles of Newtonian mechanics. And then we'll have a few examples to go through and apply those to some problems.